Hi, I'm Dominic Sanchez. I'm a PhD student at UC Santa Cruz's Department of Astronomy and Astrophysics. My research focuses on developing astronomical instrumentation to directly image planets outside of our solar system called exoplanets. By directly imaging exoplanets, we can separate the light from the star, which allows us to gather direct information from the exoplanet, such as its spectrum, so that we can later characterize its atmosphere. Ground-based optical telescopes, like the Shane telescope in Lick Observatory, take snapshots of planetary systems where they attempt to resolve the exoplanet from the host star. Unfortunately, this is rather difficult because the atmosphere distorts the incoming starlight. This light can be described and approximated as a planar surface of constant phase, or a planar wavefront. When starlight travels through the atmosphere, local temperature or pressure gradients distort the flat wavefronts, and the result is a blurry image of the planet and the host star. However, we can correct for these atmosphere-induced distortions by deploying actively correcting optical technology, called adaptive optics, which compensates for the atmospheric turbulence and restores telescope resolution. An adaptive optics system is comprised of a deformable mirror, a science camera, a control computer, and a wavefront sensor. The wavefront sensor measures the atmospheric aberrations, sends this information to the control computer, and then tells the deformable mirror to change its surface shape and reflatten the wrinkled wavefront. The science camera then collects new images during active correction and allows us to distinguish between the star and exoplanet. A prime wavefront sensor candidate to implement into the next generation of extremely large telescopes is the pyramid wavefront sensor. Traditional pyramid wavefront sensors utilize a four-sided glass prism, where light from the telescope is focused onto the pyramid apex, transmits through the glass, and produces four images of the telescope aperture, called the pupil. The light intensity distribution between these four pupil images yields information about the atmospheric aberrations, which we use for correction. These glass prisms unfortunately induce wavelength-dependent aberrations and limit the sensitivity of this device. My collaborators and I have created a three-sided reflective pyramid wavefront sensor, where instead of light transmitting through the pyramid, the light is reflected from the pyramid apex. A re-imaging mirror recollects this light and images the pupil directly behind the reflective pyramid. Drill holes are carefully positioned to allow light through unvignetted, and unlike glass, mirrors do not induce wavelength-dependent or chromatic aberrations, and they simplify the optical design of our wavefront sensor. Furthermore, the same wavefront sensor or same wavefront information can be collected with just 3 pupil images instead of 4, and as a result, it uses less detector space and pixels. This reflective design therefore mitigates chromatic aberrations, uses fewer pixels for wavefront measurements, and the three-sided pyramid geometry is easier to fabricate. I recently designed, installed, and demonstrated a three-sided reflective pyramid wavefront sensor on the Shane telescope, and we successfully performed active wavefront correction. These exciting results demonstrate proof of concept, and the sensor has the potential to be a versatile device for future implementation. Thank you to the ARCS Foundation for making this research possible.